Hi, everybody. It is May 1st. We were just chatting about how, it's finally, we've escaped March and April and we're into May. It's May 1st, a new month, and we're hopeful for things ahead. But this is calculus. This is going to be our last day of content for calculus for the spring 2020 semester. We have one more day on Monday, which we'll use for sort of general questions. So if people show up, we can review, or you can ask questions, anything that you want for that period. And so whatever we cover today, that will put a cap on what's going to be on the final exam. So I have this question right here up. So it's one of our web work questions. And so there's a few of them that are like this in web work homework. They're like fencing problems, right? So you have some sort of area that you want to enclose, and sometimes you're given a specific amount of fencing to do that, and sometimes you're given a fixed area that you want to enclose. And so what we want to do is optimize the other parameter, right? So sometimes we want to maximize area, sometimes we want to minimize the amount of fencing that we need. And in this particular question here, we have one where we want to maximize the area, right? So we're given a constraint. We have 2,100 feet of fencing, and we want to build a pen that looks something like this. And what we want to do is maximize our area. Okay, so what we're going to do is we'll sort of, I'll walk through this problem, and then we'll talk about, the different pieces of an optimization problem and how we set them up. Okay, so I'm going to switch over to the Blackboard. All right, so step one, right? So this problem, they already gave us a picture, right? So they already drew us a picture. But I went ahead and I recreated it here. But generally, when we're dealing with an optimization problem, what you want to do is you want to draw a picture and then assign variables to quantities that might change over the problem, right? So depending on how I build my pen, I could have a pen that is like really long and narrow, right? So my pen could look something like this, or alternatively, right? It could be really narrow this way, and then it could look like this, right? So lots of different options and everything in between, right? These regions could be more squares, they could be rectangles. But what we'll do is we will see and figure out what are those optimal dimensions for us. Okay, so let's go ahead and jump in here. So what we need to do is we need to figure out what are the equations that we're going to need to set up here, right? So we want two types of equations. One is a constraint, and then one is the objective, right? So our constraint is what is going to be putting restrictions on us here. We don't have unlimited resources. So we need to figure out what that constraint is. And then we have an objective function, which is the thing that we want to optimize, right? So we have two different types of things. So what is placing restrictions on us in this particular type of problem? What's our limiting factor? Yeah, fencing, right? So I have 2,100 feet of fencing. And so what I have to do is I have to think about, hey, well, this constraint, I need to have fencing on on all these sides. And so all of those side lengths have to add up to 2,100, right? So 2,100 feet of fencing has to be, well, how many X's do I have here, right? So if I put X's and Y's on all these things, it looks like I'm going to have the three vertical sides, those are Y's. So I'm going to have 3Y. And then the way this is set up, I have 1, 2, 3, looks like I have 4 X's. Okay. So this is going to be my constraint. Whatever X and Y are, they have to obey this equation. Okay, so no matter what x is or what y is, when I plug both of them in, they have to satisfy this being 2100. Okay. Now, my objective function, the thing that I want to optimize, is going to be area, right? So it looks like in this particular case, the area of this whole rectangle is going to be in two variables, right? So it's area with x and y. And I have a 2x, that's my length, and then a y is my width. Right, so setting up my equations here. So, okay. So is there anything left for us to set up? You know, I've got perimeter in there, I've got area. Doesn't seem like there's sort of any other things. So now this is the equation that we want to maximize, right? So this one right here, our objective. But the problem is it's got two variables. So for our purposes right now, we're in Calc 1, right? And so we want to get things down to a single variable if possible. And so what I'm going to do is I'm going to use this constraint to eliminate one of the variables, either x or y. Now, looking at this problem, it seems like if I knew what y was, I could solve for x, and if I knew what x was, I could solve for y. So let's just go ahead and do that. So I'm going to solve this for y, right? So I get 2100 is equal to 3y plus 4x. So 2100 minus 4x is equal to 3y. And so I get this 2100 minus 4x all over 3 is equal to y. Okay, so this is a good start. And so if I simplify this, so this becomes 700 minus 4/3 x is equal to y. Okay, so what I'll do is I'll take this, right? I'll take this for y, and then I'm gonna substitute it in over here. Okay, so I'm gonna go ahead and plug that in, and so what I'm gonna get at the end of that. So find the spot here where I can zoom. So what I'll get is a single variable equation just in x, right? So I'll get area just based on x is 2x times 700 minus 4/3 x. Okay, so what I've done is I've set up my problem and I've used a constraint to eliminate a variable, and now I have one single equation. I have this area equation, it's in one variable, and I want to find the maximum value of this. Right? So going through, what we'll do is we have to figure out, hey, is there some sort of interval that makes sense for us to optimize over? And is there, right, and then we have to find our endpoints, our critical points, and check them for our global maximum. So I'll kick it over to you. What kind of interval makes sense here? Is there a minimum value for x that we should be considering? Is there a maximum value for x that we should be considering? So what do you think? What's the smallest value that you could put in for x? 0, right? Yeah, so you could put nothing. Probably not what you want to do, right? Because you just have 3 sides that are 3 pieces of fence that are all next to each other. But it is the smallest we could do, right? So we want to optimize this on interval 0, comma, and then what's the maximum value? Could be 2100. Okay, so yeah, 2100 is going to be all of the fencing we could use, but remember, we have to put fencing in all of these spots. So how many x's are there? There's 4, right? So 4 x's. So I couldn't put 2100 at each of them. Right, I could use all the fencing on there, but I would have to divide it up equally, right? So this would be 2100 over 4. Yeah, right. So you divide it up into 4 equal spots, right? All right, so so this is the interval that I want to optimize over. Right, so what we're going to do is we'll check, right? So we'll check our critical points. The first thing we'll do is we'll take a derivative here, and I think it's going to be to my benefit to expand this first. So I get 1400x minus 8/3 x squared. Okay, so taking the derivative, we get 1400 minus this would be 16/3 x. Right? 1400 minus 16/3 x, and we want to know, hey, when is that equal to 0? Okay, so solving this, we get 1400 is equal to 16/3 x, and so x is 3 times 1400, all divided by 16. Right, so all right, so this is my critical point, and then I've got my 2 endpoints over here. All right, so far so good. We've got a critical point, we've got some endpoints, and now we just have to check them, right? So I have to check my area. So really quickly, right? So if I plug in 0 into this area, I'm going to get 0. Okay, so that sort of makes sense that if I put nothing, if I have no width here, then I'm going to have a 0 area. And similarly, if I put all of my fencing on my x's, or yeah, if I put all my fencing on my x's, I'll have no width. And then if I put all my fencing on my y's, I'll have no length. So in either case, if I plug in 0 or 2100 over 4, I'm going to get 0 here. And so my one critical point is this one right here. Now, the last thing we have to do is we have to check, hey, is this a local max or a local min? And so in this particular case, I think using the second derivative test is the easiest thing to do, right? So we take the derivative of this again, you get 0 minus 16 over 3. Okay, so this is negative. It's always negative, which means my graph is always concave down. And so my critical point should be a local max. Okay, so what this tells me is, hey, my maximum value is going to occur when x is this number right here. Right, and so I don't know if we simplify this a bit, I think this becomes x equals 2100 over 8. I think about it that way, so we could simplify further. $4,200 over 16, yeah, and then simplify like this. But yeah, quickly, let's go ahead and let's plug this thing into Desmos just to visualize what's going on here. All right, so we've got graphing, right? So our area function was this. We had 2x times 700 minus 4/3 x. Right, and we wanted to view it on the interval 0 is less or equal to x is less than or equal to, we said 2100 over 4, right? So again, in Desmos, this is not always, it doesn't always give you a nice window. So a quick check here, right? So I can I can sort of put some values in here into a table, and then I can use this zoom fit feature, which will give me a nice picture. And so what we should see is, hey, the maximum value here occurs at 2100 over 8. So let's look at what that is. 2100 over 8, 262.5 is right here, right? And so we should see that, hey, this is our x, 262.5. Our y is, or our area is 183,750. Okay, so let's go back over here, right? So this was 262.5, 183,750. And so checking in here. And so what would our y coordinate be then? So how do we go back? We still need to fill in this right here. So this is x and this is x. What's y? Right, so if we jump back over here and look at our blackboard, we actually came up with an equation for y, right? So in our work over here, we did, right? So we came up with this in blue, 700 minus 4/3 x, that's what y is equal to, okay? So we can go ahead and we could plug that, right? 700 minus 4/3 times our x value, that's gonna be what we get for our y value. Right, so it was this 700 minus 4/3 x, right? And so our x value was, we said 2100 over 8, right? So our y value should be 350. And so let's go ahead and type this in, cross our fingers, and when we can check, and then we are, looks like we're good to go. Right, so walking through that process, right? So you can see that there's a lot of different pieces that are involved in it, but the big picture was, right, we drew a picture, we had some constraints, something that was giving us some restrictions on our problem, we had an objective function, the thing that we wanted to optimize. We then used our constraint function to get rid of one of the variables, so we got down to a single variable equation, and then we used our techniques of calculus to find the optimal values, right? We found an interval on which we wanted to optimize. We took some derivatives to find our critical points. We checked our critical points and endpoints, and then that allowed us to identify maxes and mins. And so we also see that, right, Desmos is a really nice tool. If I can set it up, a lot of the time, this is the hardest part, right? So setting up our equation and then being able to see it. So if I could do this, if I can get to this point, all right, in a lot of the cases, I don't necessarily need to take the derivative. I can find my optimal values visually. But what we're going to do now is, again, we keep coming back to this idea of a parameter, right? So can we do these problems in general? You know, so if I gave you the question where we asked about, maybe I didn't need 2,100 feet of fencing, but maybe I could do it. Maybe I could do it for any number. Maybe at 10,000 feet of fencing or 1,500. Right? That 2,100 didn't seem to be such a big deal. Okay. All right. So we're going to jump into our book again, and what I would like to do, if we can, is get through these two questions today. So on our Plato page, so I have opened stuff up. So if you go to your Plato page and you click on Desmos graphs, there's two that I opened up here today. So activity 3.4.4 and 3.4.5. So if you can, right, so go to your Plato page, and then if you click on this, what it will do is it should bring up a interactive for us that we can use for our next question. Okay, so playing around with this at home, I think is going to be pretty helpful. All right, so here's the statement, right? So here's the question we're doing, 3.4.4. It says, consider the region in the xy plane that is bounded by the x-axis and the function 25 minus x squared. Okay, so in this case, I have it set up where I have, this is the function, the purple line is 25 minus x squared, and we're considering this region, right? So it's bounded by the x-axis and this line, right? So we have this sort of semicircular parabolic region that's cut off by the x-axis. So that's what we're considering. And we're building a rectangle, and we want the base to be on the x-axis, and it's going to be centered at the origin, and they extend vertically until they intersect the curve. Okay, so what we've done is we've built a rectangle, and so all we need is the base of the rectangle to be on the x-axis, and we want the corners of the rectangle to be on this curve, right? So I can extend all the way out, right? I can make a really narrow rectangle like this. I can make a tall one that's tall and skinny, right? Somewhere in the middle. And so the question becomes, hey, which rectangle has the biggest combined, let's see, which rectangle has the maximum area? Which rectangle has the greatest perimeter? And which one has the greatest combined perimeter and area? Okay, so let's see if we can answer some of these questions, right? And so then it gives us this challenge if we can do it for parameters A and B. Okay, so this is our challenge. We are going to try and optimize, find the maximum values of such a rectangle. Okay, so what do you all think? What do we think here? Like, I think our step one is taken care of, right? So we have step one is draw a picture. So we use Desmos here to draw ourselves a nice picture, and we can actually interact with it, right? We can see, hey, we have lots of possibilities. So the question becomes, well, which one's the biggest in terms of area? So where do we start? Somebody give me an idea. Yeah, so we would think that the area is going to be smaller over here, right? So the f of x, so this one, right? So our f of x that we're dealing with right now, if I just make it explicit, right? So is 25 minus x squared, right? So I'm double defining things, but yeah, this is our f of x. It's not going to give us the area, but it is going to be instrumental in finding the area. So the area is going to be the length of the base times the height. So it's not the area, but it's going to give us some information towards the area. So for this box, right? So our constraint is given by this. It's sort of baked into the problem here, our constraint. We have to be underneath this curve. So what I'm going to do is I'm going to we can draw on this, but let's see if we can figure out like what would the, in general, what would the length of the base be here, right? So in general, I want to know sort of what is this distance, right? So that's my L. And then I also, in general, I want to know this distance. That's my height, right? So if I find the area here, I need to know how tall that rectangle is. I need to know how wide it is. So how do we do that? How do I find it? So here's a hint. What are the coordinates of this blue point that I just highlighted right here? All right, so this point is going to move. It's going to change. But do we know what the coordinates of that point are? And so remember, we can't give explicit coordinates, right? Because like it's going to change. We need to sort of have a formula. Yeah, we need to have a formula that will tell us what this coordinate is. Yeah, right, exactly. Half the length, right? So whatever half the length is, that will give you, and then you could do that to find the height. Okay, so that's great, right? So the x coordinate over here is going to be half our length, right? So this is going to be half our length. That's going to be our x coordinate, right? That's going to be our x coordinate. And then how do I find the y coordinate? Oh, Sam, you said already, right? Height, right? So this is going to be the height, right? That's going to be our y coordinate, right? So if I can think about this point right here, whatever it is, but you know what we do know is it lies on this curve, right? It lies on the red line that lies on f of x. So these points, every point that's on the red curve has to have this form x comma f of x. Right, so that's the definition of being a point on this. So no matter what point I pick along the curve, it will always have this form, whatever my x coordinate is, and then f of x, right? So I plug it back into my function. Okay, so if I clear this out, right, this has to be x, right? So that'll be my x coordinate, and then whatever my height is going to be, this is going to be 25 minus x squared. Right, so I have x and then 25 minus x squared. So what we want to do is we want to come up with an area equation, right? What is the area of our rectangle based on x? Okay, so if we think about that, I'm recording some of this, and I'm going to switch over to the Blackboard so it's easier for me to write. All right. So this is what we came up with so far, right? So we have our height of our rectangle is 25 minus x squared, and then we have half of the length is x. And so it seems like I have another x over here. Right? So my area of this rectangle is going to be the length, which is 2x, times the height, which is 25 minus x squared. Okay, so 22x and then 25 minus x squared. So if I'm going to find the maximum area, right, what I need to do is I need to take the derivative of this. I need to optimize this equation, right? So we get, this is 50x minus 2x cubed. Okay, so So optimizing here, it seems like we want to optimize this on a particular interval, right? So it looks like x could be 0, right? So I could push this all the way to 0, and then x could go all the way out to wherever this point is, right? So that's whenever 25 minus x squared is 0. And so just thinking about this, that's going to be x is plus or minus 5, right? So in our diagram here, this point must be 5, 0, right? So x could go anywhere from 0 out to 5. Okay, so continuing on, right? Take our derivative. We're going to check our critical points and our endpoints. So our derivative here is 50 minus 6x squared. And so I want to know, when is this equal to 0? And again, it's a polynomial, so it doesn't have any points where it's undefined. All right, so moving through this quickly, we get 50 is 6x squared. And so this is 50 over 6 equals x squared. And so x is equal to plus or minus the square root of 50 over 6. Okay. All right, so x is plus or minus the square root of 50 over 6. Is this a max or a min? How do we know? Right, so in this case, right, so we could graph this, we could check it, but we want to make sure that we're optimizing in the right direction, right? So we still want to make sure, hey, we have 3 points we want to check, 0, 5, and then this one, right? Which, since x is going to be positive, we're only going to take the positive side of this. But as Emily pointed out earlier, when you do the second derivative, it's negative. Yeah, so let's see that, Luke, right? So a double prime, right? So our second derivative is going to be negative 12x, okay? And, right, we said we're only going to take the positive side of this. All right, so if I plug this in, as Luke said, if I take this number and I plug it into my second derivative, right, that's going to be negative. So the second derivative test tells me, hey, we're concave down, and so this is again, a local max. Okay, so our maximum should occur when x is square root of 50 over 6. Right, so let's go back to Desmos and let's see this, right? So we have our area equation here. Right, so I'm going to open up a new Desmos window. I said our area equation was 2x times 25 minus x squared. And we wanted to view this on the interval 0, 5. Right, so let's change our viewing window here. Okay, so we could do the same trick, right? So we could get a nice window relatively quickly by just using our zoom fit feature here, right? So I want to pick something else in there. And so here's our equation. We don't need this table anymore. So what we should find is that at the point square root of 50 over 6, and then a of this, we should get that maximum value, right? So that's what occurred. So second derivative test for concave down, we've got a local max there. And, you know, we could have graphed this right away, right? And then we would have got this value 2.887, which, depending on the context, may very well be good enough. But in any case, what we did is now we have the precise answer, right? So if we wanted more decimal places or whatever, we could do that. Okay, so how does this change, right? So how does this change if we add in some parameters, right? So there's nothing, again, there's nothing special over here about, you know, about 25 and 1, right? So we could do the same problem where we are, right, where we have our f of x is just on a parameter, and right, so we would have a 2-parameter function here, and then we could still optimize, right? So regardless, now effectively what I'm doing in the background here, in order for me to create this Desmos interactive, right, I've had to think about this problem in generality as well, right? So you notice that in order for these interactives to go, we have to solve these equations with parameters in them. So while Desmos is great, right, the reason that we can do a lot of these things is because we do the math in the background, and we're able to solve them in generality, regardless of what the parameters are. So these ideas of solving things in generality, that's what allows for these interactives to be built. So we have some importance there. Okay, so we've got about 7 minutes left, and I do want to get to the last question here. It involves some trigonometry. But was this okay? This felt pretty good to us? Yeah, we're good. Okay. All right, so we're going to go back over here. We'll try this last one, activity 3.4.5. Okay. So the way the problem is stated, it says you're going to create a trough, okay, and you have a piece of metal that is 4 feet by 24 feet. Right? So you've got a rectangular sheet. You know, it could be something like this. And it says 2 symmetric folds 2 feet apart will be made parallel to the longest side, so that the trough has cross section in the shape of a trapezoid. Okay. It says what angle should be folded. So what we're going to do is, if this was 4, right, you're going to imagine sort of folding up a piece of paper into a trough, and so you're going to be sort of bending it. So the question is, how far, right, how far do you want to bend your paper up to create this trough? Now, what I thought was this problem was particularly hard to visualize, especially virtually. So if you click again on our Plato page, if you go to activity 3.4.5, what I've done is I've created a virtual version of this, right? So this is our Desmos interactive here, okay? And so what we can see is, right, so we're going to take a sheet of paper. It's going to look something like this. We're going to bend up the sides, right? So we're going to bend it up to a certain point, and we can imagine that that is going to create a trough for us, right? So these 2 additional sides, if you put them in, you'll see that you could create like a basin here, right? You know, for holding stuff. It would be a box or what the author is calling a trough. Okay, so if I don't bend it at all, I don't really have a trough, and then I could bend it so maybe my sides are vertical. I would get a box, or, you know, we could bend them in more. We would get this, you know, maybe a sort of a narrow top. But the question is, you know, how far up should I bend it so that I get, you know, the maximum volume? Okay. So coming back over here, right? So it says what angle should the folds be made to produce the trough of maximum volume? All right, and so this is a trigonometry type problem. So we're gonna have to use some trigonometry here. And so let's jump over to our blackboard and then see if we can optimize here. What's going on? At least set it up. We've only got 4 minutes here, but I do want to show you sort of how we might set up such a problem, right? So they're saying that these pieces right here are 2 feet, right? So you have a piece of paper that's 4 feet wide, and so you're going to take 1 foot from each side. And you're going to bend it up at these points. It's going to be symmetric, so you get some angle here, theta, and you get some other angle here, theta, right? So there's going to be sort of the ground is over here, and then the ground is over here, right? So you're going to bend these up and create a trough. So we think about this, we would say, all right, I need sort of a lot of information, right? If I want to find the volume of this trough, so I'm going to come back here. If I'm going to find the volume of this trough, I need a lot of information, right? I need to know, hey, like what would even be a formula for the volume of this? Okay, so what we're going to need is we're going to need the area of a trapezoid, and then I'm going to need the height of this thing. Okay, so what we have here is we actually know the height, right? So the length of this is going to be 24. And so then what I need to do is I need to figure out, hey, what is the area of a trapezoid? Now, this is something that you may or may not know, but you're going to add up the lengths of the bases. So I'm going to have this length here and this length here, right? So I'm going to add those up. I'm going to cut that in half. So it's 1/2. We call this base 1 and then base 2. And then I want to know, hey, what's the height of my trapezoid, all right? So when I put all this together, we're going to have to take sort of these measurements. We're going to need to know what these are. How tall is it? And then what's the length of the 2 bases here? Okay, so let's go ahead and flip back over to our chalkboard so we can visualize this. And so quickly here, right? So if I put this in, right? So I'm going to need to know what's the length of this base 1, and then I'm going to need to know also sort of what is the height of this. And so our volume formula is going to be given by, so it's going to be in general, it's going to be the area of this trapezoid times, the length of the trapezoid, which is 1/2 base 1 plus base 2 times height times 24. Okay, so our job now is to go through and figure out what are these different values, right? So base 1 here we're gonna have in red. We need to figure out that. Base 2 is in blue. I know is 2. And then height is going to be in green. I'm going to need to figure out what this height of my trapezoid is. Okay. And so what we're going to do is we're going to do a little bit of trigonometry here. Okay. So if I were to take a triangle, I'm gonna put it in yellow here. Okay. So I'm going to pull this triangle out, theta, and this is 1. One of our facts from trigonometry is that the length of the base here is cosine of theta, and then the height of the triangle is sine of theta. Okay, so what I get here is I get this is cosine theta, and this is sine theta, and the same thing over on this side, right? I get this is cosine theta. I get this is sine theta. Okay, so it turns out that in green here, my height is going to be sine theta, and then I get 1/2, let's give us some space here. I get 1/2 times, well, my base 1, right, is going to be 2 plus 2 cosine theta. And then my base 2, we said was 2. And then we're going to multiply all of this by our length, which is 24. Okay. And so what we end up with is a volume formula based on theta, which ends up being, 24 times 1/2 is 12, and you get 2 plus 2 cosine theta plus 2 times sine theta. Okay. And so we're 2 minutes over here. So we're not going to go through the whole process of taking this derivative, but fortunately for us, we do have Desmos. And so what we can do is, if you would like to, you can sort of view this volume equation, right? So I already have it plugged in here. 2 plus, right? We have this going on, and so when you drag your trough around, you'll be able to sort of find the maximum value, right? So when our angle is 1.196 radians, that should be the optimal point, right? So you can see the volume down here is going to be 0. As the trough bends up, it's going to come to some sort of maximal volume, which will be right around here. And then if we bend it any more, we're only going to reduce our volume even further. Okay, so somewhere right in here will be our optimal point. Okay, so just going back, right? So we do have a trigonometry question on the webwork homework, but don't forget, right? Don't forget about our trigonometry principles. So we can use some of this to help us out. Okay. All right, I know that we are 3 minutes over here, but I'll kick it over to you if there's any sort of last questions about this stuff. Will there be a trigonometry one like this on the final? I don't know. Generally, the problems that I put on the final aren't the hardest ones that you've seen all year. So this one, we kind of burned through this one pretty fast. So it's unlikely that I'll give you one that's this challenging on the final. All right, so if there's no more questions, remember, so homeworks 12 and 13 are due on Sunday. I reduced them a little bit. I took 2 questions off of homework 13 that I thought nobody had done them yet, and they were pretty challenging. So I took 2 of them off to reduce your load a little bit, but we'll meet again on Monday. So again, I won't try to cover any new material, but if you show up, I'm happy to answer any questions, right? So the final will open up on Sunday. You'll have the whole week. And then Monday at our usual time, 9:20, I'll be here to answer any questions that you have along the way. Okay. So I'm going to go ahead and call it here. Have a great weekend, and email me with any questions that pop up. So thanks for showing up. You too. Have a great weekend.